It's working. Okay. All right. So for these types of problems, first derivative used to find points of inflection. All right. First derivative is used to find critical values, which are used to find minimums and maximums, or places where the function has a derivative that is 0. It's used to find intervals of increasing and decreasing. But now we're looking at this next part, which is part 3, determining concavity, determining points of inflection. So to do that, we need to find G double prime. Now, last time we discussed how we can take the derivative of this function. We can take the derivative of the alternate form, which was 1/2 times 2x minus 3 times x squared minus 3x negative 1/2 power. You can even simplify this by moving the 1/2 inside if you wanted to, and turn this into a much simpler product. But we've got to take the derivative of one of these. So I pose to you guys, would you rather do a quotient rule or a product rule? Sure, happily. So if I'm going to do the product, I'm going to distribute this 1/2 inside, giving me this slightly different function. X minus 3 over 2 times x squared minus 3x negative 1/2 power. So in this case, with this function, I'm going to label this as my left-hand piece, this is my right-hand piece. To do the product rule, I need to take the left, right, the derivative of the left, the derivative of the right, that was awful, never again, the derivative of the right, and determine what each one is, so I can plug into the product rule. Again, this is a technique you can use in order to make sure you get all the pieces right for each derivative. So for this one, my left-hand piece would be x minus 3/2. So that means the derivative of that piece would be 1. The right-hand piece would be x squared minus 3x to negative 1/2 power. The derivative of which would be a power rule with a chain inside of it. So negative 1/2 x squared minus 3x to the negative 3/2 power times 2x minus 3. Okay, let's take the derivative of g double prime. So g double prime of x is equal to product rule. Left d right plus right d left. Let's do it. Left d right remember, this entire thing is due to the right-hand side, plus right d left, so right x squared minus 3x, negative 1/2 power, times 1. So there's g double prime, and it's a product rule. And again, we can easily do the same thing with the quotient rule. It's kind of 6 of one, half dozen the other. But now comes the fun part. I need to take this function and be able to write it in a specific form where I have a way to find my zeros. Okay, I'm going to do some simplification steps. And some of them are going to seem a little strange, so I want to make sure to justify each and every one of them. I'm going to take this negative 1/2, I'm going to multiply it to this term. What that's going to do is I get x minus 3/2. The second piece stays the same, x squared minus 3x to negative 3x power. And this should become negative x plus 3. Right, 3x. Okay, and then plus x squared minus 3x to negative 1/2 power. Okay. I'm going to take these two terms, since those are each binomials with the power of 1, I'm going to multiply those together to end up with the perfect square formula. I get the following. Negative x squared plus, that would be 3x minus 904. Okay, so multiply those two terms together. Times x squared minus 3x negative 3 half power plus x squared minus 3x negative 1 half power. Whew. Okay. Once we get to here, there's some options on how we choose to solve this thing. The technique I'm going to use is a factoring technique. It's a fun one. It has to do with how we simplify these negative powers. So I'm going to take a second and do that step. Note, with these kinds of problems, when they get nasty like this, one of the first things you should note is that keep in mind the long-term goal. I want to find the zeros of this function. The ways to do that, the typical ways, is if I can find a way to solve directly or if I can factor something. So I'm now to a point where I can see that these clearly have something in both of them that I can factor. I'm going to factor this. Now I'm going to factor using the worst term, negative 3 halves. What that'll do is it'll force the nicer term, the negative 1 half, to become positive. And it'll cause this piece to actually go away. Here we go. X squared minus 3x, negative 3 half power. Okay, that's all agree what happens to the first piece. This entire thing gets factored out, so what's left behind? Negative x squared plus 3x minus 9 over 4. Now, on the second term, because I'm taking a negative 3 halves out, remember when I factor, it's the same as subtraction, so this ends up becoming plus x squared minus 3x to the positive first power. You can verify this pretty easily by just redistributing the function. If I was to redistribute this piece times this piece would be the same as up above. This piece times that piece, since they have the same base, you would add the powers together. Negative 3 halves plus 1 would be negative 1 half. These are the same thing. Now the inside can be simplified because it's the power of 1, and the outside is being multiplied, so I could eventually use the fundamental theorem of arithmetic and solve directly. Let's do it. Inside first, simplifying. I have negative x squared, positive x squared, those are going to cancel. I have 3x and negative 3x. Those are going to cancel, leaving just negative 9 over 4 times x squared minus 3x to negative 3 half power. This being multiplied. Use the fundamental theorem of arithmetic. The negative 9 over 4 does nothing because it can never equal 0. This entire thing becomes x squared minus 3x to negative 3 half power equals 0. Wow, okay. All that. This nasty, disgusting, terrible thing. Again, that. Algebra! Yay! From here, I can rewrite negative powers jump to the bottom, which becomes x squared minus 3x. The positive 3 halves power equals 0. From there, the top will never equal 0, the bottom equals 0 at 0 and 3. So there's a point of inflection. So, PYs. Yeah, wow. That's how I would phrase it too. Now, I need to determine points of concavity, so I've got that. I need to determine the interval of concavity. I need to test around these. Same way we test the intervals of increasing and decreasing. I have 0. I have 3. Need to pick numbers around it. Now, if you remember something from yesterday, you can save yourself some headaches here. One of these is useless. One of these intervals.
2.
Why the 2?
It's imaginary.
That's right, it's imaginary. So really I gotta plug in negative 1, I gotta plug in 4. Now be careful, I can plug it in too. Here, there, there, or here. I cannot plug it into this one. This one has already been solved with the fundamental theorem of arithmetic. This is not the derivative. This is a simplified version of it. I can plug it in here, or any of the ones above. I cannot plug it in down here. These are not options. Do not consider them as being possible. Okay? So I'm going to plug in here and see what happens. I plug in -1. The left-hand side ends up being positive. The right-hand side ends up being negative. So left-hand side is negative. I plug in 4. It ends up being positive. The right-hand side is negative because it will always be negative. Positive times negative makes this negative. So it is concave down. CCD, concave down. From -infinity to 0. Union 3 to infinity. Well, that's a tough problem. What about concave up? Never. It is never concave up. Because there's never a time when the second derivative is positive. It's negative here, it's imaginary here, it's negative there. It is never positive. Therefore, it cannot be concave up. And again, I can verify that pretty easily by looking at the original functions picture, because I do have graphing calculators now that can do this problem for me. But I mean, imagine if you don't have a graphing calculator, how much this still tells you. Because now I know, okay, it's concave down in these places. It's never concave up. I have clear minimums at 0 and 3 as well. So I get a pretty good image of what this thing looks like as long as I've answered all 2 parts of this problem in terms of what I can do with the first derivative and what I can do with the second derivative. I get a very clear picture of what this thing should look like, even though I haven't found exact values yet. Now, one last thing to mention, the why behind some of this. This prevents surprises. It is possible in a function that the function is nice, predictable. Take an unknown function, which I'm going to call h. If I told you the left-hand side is doing this, and the right-hand side is doing this, and said, hey, what's happening in between those two? Some of you guys might look at me and say, well, let's make a parabola out of this and make it work. Some might say, well, let's have a single squiggle in between. But if I don't know anything about the middle piece of this, with no derivatives, no ideas of how to test them, literally anything could happen in between these two. But if I told you, hey, in between these two, there's exactly one place where the derivative equals 0. That severely limits what can happen in between these 2 places. If I say, hey, there is no concavity changes in between these 2, that severely limits what this thing can do in between these things. If I tell you, hey, there's no places where the derivative is undefined in between these 2, that severely limits what this thing can do. It gives a lot more tools. And all those are just first and second derivative questions. They're just how the pieces fit together. And again, we've seen some functions in this class already that do weird things, that follow unique rules. Picture the one we had earlier in the semester. I'm going to cross my fingers. Who doesn't work today? Please. Please, Desmos. Please. It's never. Well, that's all I have. Okay. Go. Yep. Beautiful free math. Yay. If we have a weird function, something like, what do we have earlier in here? We had sine x over x. That was a weird one. you can look at a function like this one and say, okay, well, I have specific places where the derivative is defined and one place where the derivative is undefined because of how the pieces work together. You can look at this function and say, okay, well, I'm going to have certain numbers of mins and maxes, certain places where the concavity is going to change. Without having this graph, I can still tell a lot about how this function is going to act, just with the first and second derivative. So again, the idea of these derivative tests, these derivative rules, was to take the idea of graphing them before graphing calculators and be allowed to determine what they're going to look like on a most basic level. If you know for a fact that a function only has 3 zeros, 3 derivatives, that can tell you a lot about the function. If you also know, hey, it's also undefined in one place, that can tell you a lot about the function. It only has one place where the curvature changes, that can tell you a lot about the function. Each thing tells you very specific details that allow you to find more and more complex solutions. More and more details about what this thing could be acting like and could look like. Questions? Problem number 2 is harder than anything you're going to have on your test. Most of us are going to look at problem number 1. Using that particular piece to find the first and second derivative, using those pieces to find critical values, determine intervals of increasing and decreasing, points of inflection, concavity, that kind of stuff. We'll do a lot with polynomials because they're relatively easy to work with. However, those same rules can be applied to more complex functions. Okay, for today, I want to step into a new place, a new idea. This idea is referred to as implicit differentiation. A very fancy term, I'll write it on the board here in a moment. The idea is, what if you have more than one variable in the problem? How do you approach doing math like a derivative when you have more than one variable in the problem, or when your variables are not easily solved for? So let's start with a basic problem we've already done before. I'm going to tell you, hey, we have y equals x squared plus 3x minus 4. And I told you, hey, let's determine critical values. Well, we all look at this function, and it's written as y equals a function in terms of x. We take a derivative, we'd set it equal to 0, and then we'd solve, right? So if I asked you to find critical values, what do? We do y prime equals 2x plus 3. We then would take that function, set it equal to 0, and solve, and then with x equals negative 3 halves. We could then determine, based upon either what the function looks like or what the first derivative test is showing, if this is a maximum or a minimum, and we move on from there. Great, fantastic, we've done it. What if the function isn't so friendly? Like, this is nice because you notice you have the independent variables on one side. You have the dependent variable on the other. That makes this super clean because I just take y, make it into y prime, and then take the derivative on the other side with regard to x, like we've been doing all year so far. What if that's not possible? Let me draw another relatively simple equation. It's going to look very similar, where this is not possible. Y squared plus y equals x. Y plus x. If I ask you to find the critical values, we are in trouble. Because I can't do it in terms of x because there's more than one x. I can't do it in terms of y because there's more than one y. So what on earth are we supposed to do with this kind of function? Well, it turns out there's a simple way. The idea, very fancy, it is called implicit differentiation. So remember, differentiation is a term we use to describe a derivative. It's where we determine how a function is changing over time. Normally, if we talk about Newton's approach, we'd say direct differentiation. We talked about how people like Leibniz use a notation f prime. Whereas somebody like Newton used the notation dy dx. They both mean the same thing. You're taking a derivative with respect to the x variable. In this case, our x variable is the independent variable, so that makes a lot of sense. We're seeing how x is changing, so we do f prime of x, or we do dy dx. With implicit differentiation, that idea does not change. What does change is the fact that you may have more than one variable. So doing it with respect to x could become difficult. Take, for example, this problem. How on earth am I supposed to solve this thing? Well, it turns out I solve it very similar to what I would do before. I take a derivative with respect to x. The only difference is some things I can't do that with. I'm going to go back to the previous problem. We did this with Leibniz's technique, using Leibniz's notation. I'm going to do it now using Newton's notation, because that's going to help us connect to the implicit idea. Here we go. So Newton would take this function and he'd say, you know what we're going to do? We're going to take the entire function, we're going to make it change with respect to x. So what does that do? The d dx is applied to everything. So dy dx is on the left-hand side, and then we take a derivative with respect to x of the right-hand side. So watch how this works on the right-hand side. You distribute the ddx over, so we get ddx of x squared plus ddx of 3x minus ddx of 4. Now, as you do this changing, they apply the same rules we had before. The derivative of x squared, of course, is 2x. The derivative of 3x is 3. The derivative of a number, a constant, is 0. And that's where we get the 2x plus 3 from. Well, I'm going to do the same thing with this more complex formula, an implicit formula. It's implicit because our function is not directly defined by one of the variables, y by itself, or even x by itself. You can take a derivative with respect to a different variable. We spent the majority of our time in class doing it with respect to x. We've also done ones with respect to t. If we think about it, we could do it with respect to y as well. It would just be how y is changing over time, as opposed to how x is changing over time. If you had 3 variables, x, y, and z, you could do it. Let's do something terrible. You could do it with x, you could do it with y separately, or z separately. Let's talk about this function now with Newton's approach. We take this function, the derivative with respect to x. Here we go. So, just like before, I'm going to distribute it to each one of these. ddx of y squared, ddx of y equals ddx of xy, ddx of x. Okay. Well, one of these we've already done before. That right-hand side, ddx of x should be, of course, 1. That's easy. But what about these other ones that have y involved with them? Well, this is where we get the implicit definitions. Here's how it works. You take the derivative like normal, but because we don't know what y is doing or how y is acting, it's like a chain rule. Take a look. I will write the solution and then explain it afterwards. Here we go. Think about the derivative rules. If I have something squared, the derivative would be 2 times something. So if I have x squared, it becomes 2x. But what really happens is, if I have that thing being squared, it becomes 2 that thing times the derivative. Now normally this doesn't matter, okay? Side note, if I take x squared and take derivative, I should get 2x. But what I should get is actually 2x times x prime. The difference is the derivative of x by itself is 1, so it doesn't do anything. When it's a y, I don't know how y is going to act. I don't know how y is changing. So I have to have a y prime in the problem because it's not changing like 1, like x. It's changing the way y is changing, which we don't know about. It's an unknown, thus being implicit. It's acting in an unknown manner, so I have to leave it in the problem. Here, d dx of y, the derivative of a standard variable is 1. The derivative of x is 1. But really, the derivative of x should be x prime. The problem is that x prime is 1. So it turns out this one is just y prime. The derivative of y squared is 2y, y prime. The derivative of y is just y prime. Over here, we have a product. We have to do the product rule. Left d right plus right d left. One piece at a time. Left d right plus right d left. Simplifying. So notice there's two different versions of y. There's y and there's y prime. Two different things that have to be treated as separate variables. Because one's the y values. Remember, it's the heights. It's the y-axis. One's y prime, which is how y is changing, an unknown. So watch how this is written. 2y y prime plus y prime equals x y prime plus y plus 1. Okay. My goal is to find the derivative. It turns out, the way you do that, I want to find out what y prime is. In other words, I need to get y prime by itself. Take a look at this problem. There are 3 variables. Y prime, x. I tell you, we need to get y prime by itself. How do I do that for this function?
You pull out y prime on one side.
You would be correct, but there's actually y prime on both sides. Can I make some algebraic adjustments here?
Subtract the y on the left side.
I'm going to subtract this y prime over. Give me all the y primes on one side, so 2y y prime plus y prime minus xy prime equals y plus 1. And then right, we can factor now. Let's factor y prime out. If I factor y prime out, what's left behind on the left-hand side?
2y plus 1 is x.
Very good. Equals y plus 1.
Divide 2y plus 1 by x.
Yep. I want to get y prime by itself, so I have to divide by everything else. I end up with y plus 1 on top over 2y plus 1 minus x. As weird as this seems, this is a derivative. It's a derivative where both x and y are allowed to change. Therefore, we have both x and y in the solution. Now, we'll get a lot of practice with this, but I want to go ahead and extend this more. What if I wanted to find the slope? Well, normally, if I want to find the slope, I need the derivative, which I now have, and I got to plug into that derivative. But because this derivative contains both x's and y's, I'd have to plug in both an x and a y value. Because, unlike with other standard equations, these equations are not functions. Go back. Here. This is my original equation, right? Y squared plus y equals xy plus x. This is not a function. What do I mean? From Algebra 2, the definition of functions, it must pass the vertical line test. This fails. Let's pull the function up. That can also be helpful here. Remind me. Y squared plus y equals xy plus x. There we go. y squared plus y, y squared plus y equals xy plus x?
Yeah.
Well, Desmond will not do it. I'd be very upset if Desmond will not do it. No. No.
It's the smaller from X. Yeah.
Did I make a mistake?
Yeah. But I don't think no, this is because you can factor out a y on that side and get y plus 1.
Oh my god, it was supposed to be. Oh my, I'm so stupid. Oh my god, it's supposed to be 2x. God damn it.
Oh. That makes more sense now. Yeah, because I solved it at the beginning. I was like, wait. Then you got y equals x. Yeah, I was like, wait a second. Did I just mess something up?
Dang it. Okay, well. Okay, so we found the. We found the. You get the idea. We'll work through a bunch, but notice that this breaks function rules. So if I want to find the slope, I can't just define it by the x value because there's more than one x value. I have to define it by both the x and the y because I could be talking about the x value at 20. Well, this thing's like freaking out because it's not like this. I could be talking about the x value at -2 here, or the x value at -2 down there. So I have to define it with both x and y. So that's why x and y end up in the derivative. Because these are not functions anymore. This is the idea of implicit differentiation. It looks at functions and says, hey, these are not standard. So we have to have ways of still talking about them. Now, there are some common ones of these we'll talk about in this class. You cannot take a standard derivative with them. You just can't, because there's no way to get y by itself. If we look at this function, not the one I made a mistake on, there is no way to get y by itself. There's no factoring, there's no fundamental theorem of arithmetic, there's no fancy rewrites. Y never gets by itself. You think y is by itself, there's another y hidden over in the corner. Okay? It's like herding cats. You can't get y on its own. So y ends up in our solution. This is the idea of implicit differentiation. Is let's take more and more complex problems, functions, or equations that are non-functions, and still be able to talk about their derivatives, their slopes. Be able to talk about their critical values. Some common ones. There's a lot of fancy names. I'll show some more tomorrow. Lambda escape is one of the more common ones we'll talk about. Infinity symbols. These things you cannot possibly define with just y by itself. It's always going to have more than one type because it's not a function. So I have to have both x and y in the derivative. If we just spoke about in this picture when the x value is a half. I could be dealing with a positive slope if I'm talking about this half. Or I could be dealing with a negative slope if I'm talking about the other half. So I have to have both components. The nice thing is, in general, these follow the exact same rules, meaning the product rule works the same, the quotient rule works the same, the chain rule works the same, the power rules all work the same, the sum difference rules, everything we've already been doing works the same. But now if you ask the derivative of y, you're going to eventually end up with a y prime. Let's talk about some basic rules. So, we talked yesterday about how u substitution is going to become really common. I'm going to write all of these in terms of u now, because when we talk about our rules, now we can also have these other components in them where I'm not sure if it's a variable in charge of x or a variable with y instead. So, the standard rules. The derivative with respect to x of u is u prime. But think about it. If u is the same as x, do a simple substitution. Derivative with respect to x would be x prime, but x prime is 1. We know that already from what we've already discussed, our rules. The derivative with respect to x of u squared is 2u times u prime. It's a chain rule. In fact, the chain rule is the first time you see any components that act like implicit differentiation. To the third, same concept. It'd be 3u squared times u prime. And again, if I just replace u with x, everything comes out the exact same. Nothing changes. Because x prime is just 1, and then I'd have x cubed becomes 3x squared times 1, the exact thing we've already discussed. Your basic products. So let's say I take the derivative with respect to x of u times v. It's v left d right plus right d left. And again, if you think of these as anything we've discussed so far, all these rules are the same. It's just now we could have a y. Nothing changes. Just now we could have a y instead. And so we have to consider the possibility of a y prime. This is also how you treat things like, what if I want to take a derivative with respect to a different variable? Like, let's say I don't want to take a derivative with respect to x. I want to take a derivative with respect to y. See how the y values are changing over time. Well, in that case, d dy of x is unknown. That's how the variable is changing. That's what you're trying to find, actually. Quotient rule, same way. Chain rule, same way. Again, because I don't know how each of these variables is working, this gives me a general rule that works for both x and any other variables. Free radicals. The general power rule works still. Just make sure now there's a chance you'll have u prime. Every rule we've discussed so far can now be done implicitly and nothing changes. It has the same basic process. It's just now it's a possibility that maybe we're not just taking derivative of x's. We can now have also y's. Common formulas you might already know: ellipses, circles, because they have both x and y as variables. Now we can find those derivatives. We just have to do it implicitly. Note, the common process we had to do that with was to take the derivative implicitly and then solve for y prime. Because remember, y prime is the derivative. And so if we find y prime, we have found the slope generating function. They just have y. I'm sure I'm probably forgetting a couple of rules, but we'll go through this again tomorrow, hopefully with the other two people here normal here. But the idea is we are no longer limited by a single variable. That is why if you look at the name of this class, it's called multivariable calculus. This is the end goal. You want to be able to take a derivative with more than one variable. Turns out it's no different than taking it with one variable. It's just y prime here, because we don't know what the derivative is doing when the second variable approaches. Let's do one more simple implicit one to finish up today. Keep it nice, short, and sweet. Here you go. This function. This is one that can be solved in a direct method. You just have to take time to set y by itself. It has to do some moving of pieces around, some factoring, and some division. This could be solved directly. I would have to get y isolated. But I'm going to practice my implicit rules. So here we go. I take the derivative. So on the left-hand side, I have a product of two variables. I use the product rule. The product rule states left d right derivative of x is 1 plus right d left derivative of y is y prime. On the right-hand side, y derivatives is y prime. So the derivative of a constant is 0. I now move to get the y primes together so I can factor and isolate. I'm going to move this piece over by subtracting xy prime. Don't forget, y and y prime are completely separate. One is the variable, one is the slope of that variable. They are treated separately. I factor y prime out. It leaves me with y equals y prime times 1 minus x. I divide to get x by itself. Sorry, to get y prime by itself. I end up with y prime equals y over 1 minus x. A slope with both x and y in it. Done the exact same way we've done every other rule. Just now, when I take a derivative, I have to consider which variable am I taking the derivative of. Am I taking it with x, or do I have y's involved? And if I have y's, I end up having y primes. We'll talk some more about implicit differentiation tomorrow. You guys have a good rest of the day. We'll look at some more fancy functions that have multiple variables. The graphs are really neat looking. You'll like some of them. Not that you like the derivative, but you'll at least like the function.